All right, folks, this is another redone lecture for a class recording that failed to actually record audio. So we're talking about linear free energy relationships, and this is a way of understanding the influence of structure on the structure of starting materials on the characters and qualities of the transition state. And it's a way of thinking about the impact of electron donating versus withdrawing groups on equilibrium constant and reaction rate. A linear free energy relationship basically comes from the idea that um, free energies are additive, whereas equilibrium constants are multiplicative. So you need you need a logarithm of the equilibrium constant in order to have a linear relationship between free energies. So let me set up the situation. The idea behind linear free energy relationships is to explore the impact of a substituent on a reaction and determine what the character of the transition state of the reaction is. So to begin with, we have to establish a reference reaction and also establish some parameters related to that reference reaction. So the reference reaction is the deprotonation by water of benzoic acid. And you'll recognize this as um, really just the setup that we get the Ka of benzoic acid from. All right. And we can measure the equilibrium constant for that reaction. We'll call that large KH. And then we can measure the equilibrium constant for a series of related reactions in which we vary the identity of the substituent at the para position. And that equilibrium constant will be Kx. And then we're going to compare those equilibrium constants. And the hypothesis is that the substituent effect and changing from hydrogen to some substituent should have some linear impact on the free energy of these reactions, and that impact should be transferable to other situations. So, as an example, we're gonna run this reaction for all kinds of different substituents X, and then for each substituent X, we're going to generate a parameter called sigma X. This is the so-called Hammett parameter. And that's going to be equal to the log of K with hydrogen. Nope, got it wrong. It's going to be equal to the log of the equilibrium constant with our substituent divided by the equilibrium constant with hydrogen. Just as a brief review, the logarithm of 1 is 0. The logarithm of 1 over 10 is -1. The logarithm of 10 is 1. The logarithm of 100 or 1,000 is 3, and so on. So I'm going to show you the results for these experiments because the values for sigma that we are going to generate are often called sigma para because the substituent's at the para position. Some of what we talk about here is going to relate to intuition you've developed because of your experience with electrophilic aromatic substitution reactions and understanding electron withdrawing versus donating groups. And some of those trends correlate with what we're going to see for trends in sigma para. And sigma para basically tells you how much in terms of kcals per mole, or rather in a form that's related to free energy at least, how much more favorable it is to deprotonate benzoic acid when you have this substituent in place. All right. So we'll start with this amino group substituent, and the sigma para value there is negative by 0.66. If the log is negative, that means Kx is less than Kh, meaning that putting the amino group on the benzoic acid is actually makes the equilibrium constant lower. Okay? And we see similar things for other electronegative heteroatoms that are attached to a benzene ring. For example, hydroxide has a minus 0.38 sigma para value. Methoxide is almost the same. Now let's try to figure out why we might expect these substituents to make benzoic acid deprotonation less favorable. And to do this, we need to focus on the conjugate base. So let me draw the conjugate base, benzoate, with the amino group at the para position. And if Kx is less than Kh, the conjugate base of the para-amino benzoic acid should be less stable than the conjugate base of benzoic acid. All right, so why might that be? And if you're already sort of thinking of some things you learned with electrophilic aromatic substitution, you should be able to see that by resonance, we can donate electron density from the nitrogen into the benzene ring. Now, that amino group is not conjugated to the carboxylic acid group. Nevertheless, it can place a negative charge on the atom directly adjacent to the carboxylic acid. So we can put a negative charge on this carbon, and increasing the electron density in the ring should be destabilizing to this negative charge. Remember, stabilizing a conjugate base often involves spreading out electron density, not pushing more extra electron density toward the place that has a negative charge in the conjugate base. So one of the things we notice about groups that have negative sigma para groups is that these tend to be electron donating groups. Why do you suppose the sigma para value for NH2 is more negative than the sigma para value for OH? And the answer is nitrogen is a better electron donating group. So one of the trends with sigma para values is that more negative values of sigma para correspond to being a better electron donating group. And nitrogen's a better donor than oxygen because nitrogen's less electronegative. Its electrons are higher in energy than oxygen's, and so better able to donate. Okay, now some other familiar players show up on this list, including groups that are inductive donors. So the T-butyl group, we're getting to sigma para values that are pretty close to zero, which means that the equilibrium constant is about the same as it is for benzoic acid. It turns out that whether you have the T-butyl group or the methyl group doesn't matter much in terms of the sigma para value. Interestingly, if we take the amino group and instead convert it to an amide, the presence of this nearby carbonyl sort of ties up these lone pairs in resonance and prevents them from being as good at donating into the benzene ring as they were with the unprotected or unmodified amine. And indeed, the sigma para value for that amide group is 0. And this is sort of our intermediate or break-even point where the equilibrium constant for our substituent is equal to that for the regular benzoic acid. And of course, it's saying the same thing to put proton on this list. That's like saying KH is equal to KH, which is sort of, like, duh. Then as we go to other substituents that you might start recognizing as electron withdrawing groups, say a carbonyl adjacent to the benzene ring, that has a sigma para value of 0.47. And again, you might ask, how does that impact the stability of the conjugate base? I'm going to draw the para acetyl benzoic acid and show you that by resonance I can place a positive charge. And I'm only going to draw one of these resonance structures. There are others that we could draw, right? By resonance, I can put a positive charge in the ring adjacent to the benzoic acid, or adjacent to the carboxylate group in the conjugate base of the benzoic acid. That's going to stabilize this negative charge. If you have an electron-poor carbon adjacent to a carboxylic acid group, that should pull electron density away via an inductive effect. Okay? So you would expect, in this case, because of that electron withdrawing effect, that Kx is now greater than Kh. And that's why our sigma para values are now positive. And sort of from here on out, we're going to call this an electron withdrawing group. And the better a group is at withdrawing electron density, the higher, the more positive, the greater the magnitude of the sigma para value. So trifluoromethyl is a little bit better than, say, the carbonyl. Nitro is even better than trifluoromethyl and better than the carbonyl. And then one of the best electron withdrawing groups is the trimethyl ammonium group, where all you've got is the electron deficiency of that nitrogen. There's no lone pair adjacent to the atom to donate into the ring, and that is a very effective electron withdrawing group. Okay, so with this in mind, we have, based on this benzoic acid reference reaction, we have some parameters that describe the ability of a substituent to be an electron donating versus withdrawing group. Okay? So now we can use this reference reaction to interrogate other reactions. So, and we can do this with equilibrium constants or with rate constants. Let's start out with a related equilibrium constant. Let's imagine our so-called test reaction, not our reference reaction, is now with phenylacetic acid in which we have a CH2 group between the carboxylic acid group and the benzene ring, instead of having the carboxylic acid group directly attached to the benzene ring. And again, we'd be measuring these equilibrium constants for deprotonation of the phenylacetic acid, and we'd be thinking about this mostly in terms of the stability of the conjugate base. And one question you might ask is, how do you expect the electron donating versus withdrawing group to matter as much as it did for regular benzoic acid. And based on your intuition, you might think that removing the carboxylate 1CH2 unit further away from the benzene ring and the substituent would make the X group matter less. And so the way we test that is that we'll make a bunch of variants where we vary what the identity of X is, and then we measure Kx and generate values for log of Kx over Kh for our phenylacetic acid reaction. Okay? And so once we do this, we can generate what's called a Hammett plot. And in a Hammett plot, on the y-axis, we apply, graph the measured values for log Kx over Kh for our test reaction. And then on the x-axis, we plot the sigma para values, which are the log Kx over Kh for the reference reaction, which is, as you recall, benzoic acid deprotonation. Okay, so and then we plot these data points against each other. Now, suppose we see a situation where the slope of this plot equals 1. Then we would conclude and we're going to give the slope actually a symbol, and that is the Greek letter rho. If slope equals 1, then we conclude that our test reaction depends on substituent identity X in the same way as does the benzoic acid reaction, or our reference reaction. And in this case, that would be consistent with the ability of X to stabilize versus destabilize a negatively charged intermediate. And if slope equals 1, we conclude that maybe it depends on X to the same extent. It is similarly dependent on the ability of X to stabilize versus destabilize a negative charge. Okay? If, in contrast, we observe that the slope is between one and 0, then we conclude test reaction still involves negative charge, but X matters less. And why might it matter less? Remoteness of X and the charge. It might also be a smaller amount of charge. If rho equals 0, all right, I'm not sure I'm drawing this really good. So, dun, dun, dun. Liked it better before. So in orange will be our line where the slope is still positive, but where our slope is positive, but so there's still a buildup of negative charge in the transition state of the rate determining step, but the substituent matters less. In gray, we'll do an example where slope equals 0, and that tells you that the x substituent doesn't matter. Either, again, because of remoteness or because perhaps there's no negative charge in the transition state. If, in contrast, we do an experiment where slope is negative, if rho is less than 0, we infer that x matters, but due to a buildup of positive charge, because x matters in a way that is opposite to what happens in the benzoic acid reference reaction. Okay, so for phenylacetic acid, we would predict that we're in this situation where rho is less than 1 but is still greater than 0. In other words, this reaction involves a negative charge, but it matters less than in benzoic acid. Okay, so let me show you just a few examples of some other reactions you can analyze this way. One of them is the solvolysis of this benzyl chloride. Oops, somehow I'm getting away from the pencil functionality. So here's H, and here is another benzene ring. And we're going to measure the solvolysis rate in ethanol. Essentially, this is an SN1 reaction. And we're going to measure the rate constant for this reaction, and we'll call it Kx. And we'll be looking for the formation of this substitution product. But if the mechanism is SN1, that rate, the rate determining step, is the formation of this carbocation. Positive charge on that benzylic carbon. Okay? So, and because this is uphill in energy, you expect the transition state to be carbocation-like. That's a restatement of the Hammond postulate. And what we observe for this reaction is that little kx is greater than little kh for methoxy, but little kx is less than little kh for nitro. In other words, log of kx over kh for methoxy is greater than 1. Log of kx over kh for nitro is less than 1. Now, going back and comparing that for benzoic acid, remember sigma para for benzoic acid for the methoxy group, we can go back to the table on the previous page, is minus 0.38. And sigma para for nitro was positive 0.80. So you can see that we expect for this reaction where there's a buildup of positive charge, we expect our measured values of log k x over kh to be opposite in sign as the corresponding substituent sigma para values. So if we were to plot for this reaction, again, sigma para, which comes from the benzoic acid and involves buildup of negative charge, and then we plot log little k x over little kh for this SN1 solvolysis reaction. For methoxy that has, let's let this be the 0 point, and let's this be the 0 point on this axis. Methoxy has a positive value in our SN1 reaction. So, and I'm not sure by how much, let's just put it here. Whereas, and then the 0 point would be for hydrogen, whereas nitro has a negative value in our SN1 reaction, but a positive sigma para. And so nitro would be down here somewhere, and we would be in the situation where we would predict rho matters. We predict the substituent matters a lot because in this case, the substituent has the potential to be directly conjugated to that positive charge. So the magnitude of rho may be greater than 1, but rho itself should be negative because the SN1 reaction depends on a positively charged intermediate or a transition state in which positive charge is building up, whereas the reference benzoic acid reaction involves buildup of a negative charge. All right. The last thing I want to do is in this lecture is to present you with one last example, and we'll look at what the data tell us for what rho is, and then see if we can rationalize which of a couple of possible mechanisms might be most important or most consistent with the data. This reaction is going to be the conversion of this carbamate into the phenolate leaving group. And this other species, which I think is an isocyanate, but I could be wrong. I'm embarrassed if I'm wrong, but oh well. We can look it up. Okay. And the measured rho value for this reaction is 3. So right away, that tells us two things. First, and let's just imagine we're measuring the rate of the reaction. The rate of the reaction depends on X in a similar way as did equilibrium constant for the benzoic acid reaction. And therefore, the transition state of the rate determining step for our reaction must involve buildup of negative charge. The fact, and second, because rho equals 3, X and the negative charge matter more for this test reaction than for benzoic acid. Okay. So let's see a couple of possible mechanisms. Mechanism A is that you take your starting material and the first step is fast and probably reversible. And that is OH minus removes a proton. And then that generates, of course, water and the conjugate base of our starting material. And then in a subsequent fast step, in a subsequent slow step, that is the rate determining step, these electrons kick down here and we release the phenolate leaving group. All right. A second proposal, mechanism B, is to imitate conventional carbonyl chemistry more closely. So this would involve hydroxide acting as a nucleophile to attack the carbonyl carbon. And it would be anticipated that this nucleophilic attack would be the slow step, the rate determining step, and that would generate a tetrahedral intermediate that would look like this. And then electrons. Oh, I've drawn the wrong thing, haven't I? My apologies. Oxygen, then our phenolate group. And then in a not rate determining step, electrons kick down and that leaving group leaves to give us this weird carbamic acid and our phenolate leaving group, which would then go on to generate our isocyanide product in the next, our isocyanate, I can't remember what it's called, product in the next step. But the point is that the rate determining step here involves release of the phenolate ion, whereas the rate determining step here involves making a negatively charged tetrahedral intermediate. So let's look at both of our conclusions from the data and see which of those match which mechanistic hypothesis, if not both. First, rate depends on a similar, the fact that rho is positive means the rate of this reaction depends on X in a similar way as did equilibrium constant for benzoic acid. That is, the transition state should involve buildup of negative charge. Well, that's true for mechanism A, where there's a buildup of negative charge on the phenolate ion as the reaction's proceeding. It's also true for B, where there's a buildup of negative charge on the oxygen of the tetrahedral intermediate. So the fact that rho is positive could be consistent with both of these. Now, the fact that rho is 3 and of such high magnitude means that the substituent matters more for this test reaction than for benzoic acid. Recall that for benzoic acid, the effect of the substituent is sort of related to resonance, but sort of not, in the sense that the thing that has the negative charge is not directly conjugated to the substituent X. And so, though by resonance we can put negative or positive charges into the benzene ring, we can't delocalize the negative charge on the carboxylate into the ring. In contrast, for the reaction, for one of the reactions, for the reactions shown below, you have a phenolate leaving group where this negatively charged oxygen is directly attached, directly conjugated, so the impact of that substituent should be higher in magnitude. Now, in mechanism A, formation of that phenolate ion is involved in the rate determining step. In mechanism B, formation of the phenolate ion is not involved in the rate determining step. So mechanism A is more consistent with the data, wherein we expect having this phenolate ion formation to be involved in the rate determining step to lead to a positive rho value and one that is greater in magnitude than the rho value for the benzoic acid reference reaction.